Oh, good evening, everybody. Happy Saturday evening. Let's start with the exercise, shall we? Yeah. Uh, Exercise always good. All right. So, yeah, we'll do some leg exercise, okay? So, calf, toe lifting. Okay. Ah, ooh. Okay. Now, squat, thigh exercise. Ah. Oh. Wow. Okay. One more round of calf. All right, the other foot. Okay, finally, thigh exercise. Wow. Okay, how long did it take us? 4 5 minutes. Very good. We'll take 5 minutes break. Oh man. Whew. Good exercise. Okay. Oh. Yeah, so um, let's grab a whiteboard and see the bigger fish to fry. Okay. Yeah, it turns out that it's a special case of Fermat's little theorem. Yeah, so it's Fermat's little theorem. It's been proven many different ways. So, and the way I approach proving this, yeah, I kind of copycat from modular arithmetic. Yeah, the way one of the ways they proved Fermat's little theorem, I studied that. Okay, so yeah, it's just different expression we are doing row algebra. You are using row algebra language, but the theorem we're going to prove here is a special case of Fermat's little theorem, where in Fermat's little theorem, it's like, let's grab some pens and I'll show you. Fermat's little theorem is this. In row algebra language, um, a to the pth row p is same as a row p. And if a is less than p, p is prime number, okay? When a is less than p, r here, then yeah, r row p is equal to r. That's remainder, right? So it's a special case of Fermat's little theorem. And okay, so how do you prove this? Uh, Here we prove the distribution rule, right? Yeah, that's done and over with. So this is what we want to prove, okay? So special case of Fermat's little theorem, and proof, yeah, it goes the same way, just like in proving Fermat's little theorem, but perhaps a little bit easier because it's a special case, right? Yeah, that's good enough for us, right? Yeah. Why? Because we are not professional mathematicians. We don't have to do something too difficult. Okay, we are amateurs. I mean, I am at least. Okay, so just want to have fun. Yeah. Grab some water and. Uh, Give me a second, okay? Let me chat with my friends a little bit. Social messaging. Ah, okay. Okay. That's good. Alright. So, yeah, the way they proved this Fermat's little theorem, well, it's a special case because we're putting the base of this power to be less than p to make it easier to prove. Okay, so and why? there's no need for us to do something too difficult. Okay, so yeah, so the way they proved is using this binomial expansion and the stuff like that. Okay, so we'll do that. Okay, so well, let's problem statement. Uh, R to the pth rho p is this equal to R? Okay, so it's special case of Fermat's little theorem, alright? So we'll put this is left hand side and this is right hand side. Okay, so proof. It's mathematical induction. Okay, so where p is a prime, the set of primes. Okay, so R is less than p. Okay, period. The first case, we're doing mathematical induction. Okay, so first case when R is zero, of course, yeah, zero rho p is equal to zero. Okay, so this conjecture holds true when the very first case when R is equal to zero. Okay, okay. Second case, assume that uh, this whole thing is true when okay, what we need to prove is this. Okay, when R is equal to k, okay, k to the pth rho p, we assume that, okay, and then we can derive when k plus first the pth rho p is equal to k plus 1. If we can prove this proposition, then we are done. Okay, so okay, that's how it goes in the mathematical induction. All right, it's like domino. Okay, when one it holds true for zero, and we assume that, and then it holds true for case one. When case one, then 1 to 2, 2 to 3. Mathematical induction is like domino. Okay, all right. So all right. So here we have assumption, and here is the you have precedent and consequent. Okay, it's a propositional logic. Like if A then B, right? So this we have this if then statement. That's proposition. First order logic. Okay, if this is true, then this is true. Okay, so assumption, premise, antecedent, and your consequent or subsequent. Okay, propositional logic. So like before, okay, you have left hand side, right hand side, and here you have R1, R2, and you have L1 and L2. Okay, all right, just like before. Okay. we have here some condition, okay, where k plus 1 is less than p, okay, to make things easier. All right, so yeah, okay. Now note that k plus 1 to the pth is equal to binomial expansion, okay, so k to the pth plus plus 1, right? And all the terms except the very last one contains k to the pth or k to the some power. Okay? So this is equal to a k times some number m plus 1. Okay? Binomial expansion. Then R1 becomes, plug that in, right? Yeah. Km plus 1 to the p, well, rho p. Okay? Okay. And using the distribution rule, one rho p, and p is a prime number, so 1 is less than p, so just 1, right? Yeah. Somehow it's not quite working. Okay, so hmm. Let me look at what I did some previous test whiteboards somewhere. Okay. Hmm. Oh, I see. Yeah, took a different approach back there. Okay, okay, okay. Yeah. Okay. Yeah, this approach quite didn't work, so let's take different approach. I'm just copying from what I did in the past. So, k also k plus 1 there will less than p, okay? So, all right. Then let, because k is less than p, okay? Let k to be equal to p minus some number l, okay? K is less than p, it's like remainder, okay? So then we can express k in terms of p minus l, where l is 1 through p, right? Because k can be 0, right? Yeah, okay. Then uh, I'm not sure if I even proved that thing right or not. I'm such a lousy mathematician, okay? Because I'm so just amateur, so I'm not sure if I even proved that. I thought I did, but looking back, I mean, well, first of all, there's confusion of these symbols. So let me share with you what I did in the past. Okay, I may have made some error. All right, so we will see. So, okay, yeah, please forgive me about this confusion of all these different symbols, letters. So, I is like remainder, okay? So, if you assume this equation is true for R, what we gotta do is then R plus 1 is true, right? So if you assume that R is equal to P minus K, right? And R to the pth, that's P minus K to the pth, it becomes P to the pth, binomial expansion, blah, 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 and K to the pth plus or minus, whatever, right? Uh, and then if we do conduct rho to the p, I mean rho p on both sides, and rho p, because all the previous terms contain p, right? So rho p, the last term remains. So k to the fifth rho p is equal to r, right? So once we have that, okay. And the next step, I is equal to p minus k, right? So p minus k plus 1, right? If you do binary expansion, then yeah, I omitted the middle terms here. You have some p minus k times m, and here you have, yeah, p minus k to the fifth plus and plus 1. So, yeah, elimination lemma. Okay. Ah, boy. So this right hand side becomes r times m plus 1 rho p. Okay. All right. I think we may need some more ammunition, okay? How does this row algebra behave when it comes to multiplication? Does it distribute? Um, yeah, I may have to look up this table of this modular arithmetic a little bit, okay? So, Let's go to this brilliant.org. Very good website. Okay. Multiplication. Okay. Okay. Well, okay. So it's kind of distributive. Okay. Very good. All right. All right. All right. Yeah. Let's slow down. Okay. So because we need to step back a little bit. All right. So um, let's take 5 minutes break. And I'm sorry, I'm such a lousy mathematician. Well, yeah, I'm amateur. So let's take 5 minutes break. Okay, and then we'll step back and explore the multiplication property of raw algebra. Okay. Yeah, I just copied from modular arithmetic, and they do have some good stuff there. So okay. All right, we'll take 5 minutes. Okay. All right. Okay. Yeah. So modular arithmetic, we are just expressing modular arithmetic basically to our own language, raw algebra, right? Yeah, that's what we're doing for fun. Okay. By the way, we love black people. We love African Americans. They're beautiful people, right? Yeah. If you actually go to Africa or look at the picture, yeah, black people, Africans, they're very beautiful people. Like like beautiful night sky, pitch black. Well, my hair is black. I'm Asian, right? Yeah, I don't dye my hair. It's just my natural hair. I have some white hair here and there, but so I'm aging. All right. But yeah, black is very beautiful color. Like you have black pearl, which is kind of gray, and then you have black jaguar, black panther, right? Yeah, very beautiful animals. Beautiful night sky. Yeah, there's beauty in blacks. Okay, we love black people. They're cool. It's just that we oppose BLM ideology because it's kind of became very weird lately, right? Yeah, but we love African Americans. We love black people. We love Africa, beautiful tradition and everything. Okay. All right. And when it comes to feeding animals, I wrote down some notes. Okay, so I think people should be allowed to feed animals. Okay, I there's some regulation against that, and I think that's very unnecessary regulations. I think it's beautiful interaction between people and wild animals. So animal feeding because dogs. There's some news article about that. How did dogs originated? They say some cavemen, our ancestors way back in the days, cavemen, they fed wolves with extra meat and they became dogs. Domesticated foxes, domesticated wolves. It started from caveman people feeding wild animals like wolves, foxes. Okay? So I think feeding wild animals, I think it should be allowed. I think it's beautiful interaction because I heard some people they fed carrots off just off their window to feed some moose. Okay, I think it's beautiful. Okay, okay. So proposition. Okay, A times B rho D is this same as A rho D times B rho D rho D. You know, that's funny. In Alaska, in downtown Anchorage, okay, there's this annual tradition. They call it Rondi. Why? Well, short nickname of rendezvous. Rendezvous. This French word, right? Yeah, like rendezvous point. They meet again, right? They call it Rondi. Isn't it kind of cute? Anyway, so we have Rodi, okay? So sounds similar. Couldn't have noticing, okay? So is this true or not? I don't know, okay? But it seems to be true based on this modular arithmetic properties in brilliant.org. Well, let's see, right? Proof or disproof, whatever. I don't know if this is true or not. Okay? Let's just expand. Yeah, just like before. A is equal to Q1 D plus I1. Okay? Okay, so this is left hand side. right hand side. All right. Before that, note that A times B is equal to, yeah, just expand multiplication distributed. Okay, so and then we have D times Q1 Q2 plus R1 Q2. There's some beauty in this, kind of symmetric, right? R2 Q1 plus R1 times R2. Okay. Then left hand side becomes, yeah, this number we call it M. Okay, so D times M plus R1 times R2 rho D. By elimination lemma, yeah, D times M, it disappears. This is same as R1 R2 rho D. Okay. Right hand side, I think we're almost done here. Okay. A rho D, that's R1. Okay. Times B rho D, that's R2 by definition, right? Which is same as left hand side. So that's the proof. Okay. Yeah. So we got it. Okay. Now we can get back to that proof. Okay. So I am not sure if I can prove that special case of Fermat's little theorem or not. I don't know. I don't. Let's look up Fermat's little theorem proof. Okay. I gotta cheat. Okay. So because I'm not sure if I can prove this or not. Okay. So I mean the Fermat's little theorem. Let's go to brilliant.org. How did I prove this thing? And Fermat's little theorem itself is a special case of Euler's theorem. Okay, yeah. We are working on our ladder, okay, so proof by induction. Uh-huh. Yeah. Okay. I see. So that's how they proved it, huh? Okay. Okay. Yeah. I kind of see what they're doing here. Okay. In Fermat's little theorem proof by mathematical induction in the brilliant.org. Okay. Okay. They're using this binomial expansion and also binomial coefficient. Okay, to vanish the middle term. Okay, I see. All right. All right. So, uh, like NCR, right? Binomial coefficient. Okay, so that's NPR divided by R factorial, where NPR is equal to it's like descending multiple, like NPR is equal to n times n minus one times dot times um, n minus r plus one. Okay, which is equal to n factorial divided by n minus r factorial. So this whole thing becomes n factorial divided by r factorial n minus r factorial. Uh, and okay, let's construct Pascal's triangle just a little bit. Okay, binomial coefficient. Okay, so one, one, one. Okay. Very interesting thing is this. All right, from what I read from that brilliant.org, um, when a plus b to the n, and when n this power is prime number. All the middle terms. You see, you have 3, 5, 7. All the middle terms are multiple of that prime number, which is very interesting. I didn't notice that before. Yeah, sorry about this brightness. And they explain why very briefly, and I'm trying to understand why that's the case. They say this denominator, right? I mean, numerator is divisible by this n, but denominator is not divisible by n. I'm kind of wondering why that's the case. So you have prime number, right? And some numbers less than prime number. Okay, okay. Oh, I see. I kind of see why. Okay, so okay. Because number is prime number. It doesn't have any factors in them. Okay, so any numbers less than prime number, which is all this, yeah, you will not have any common factor with prime number. Because prime number is prime number. It has no factor, right? Now I see why. Okay. That's interesting. Let's take 5 minutes break, okay? And then I will share with you what I just learned. Okay, so this is really cool stuff. Yeah, modular arithmetic is worthwhile to educate to future generation because yeah, the cryptography, encryption, it does have some practical application. Okay, modular arithmetic. When we calculate big numbers, we can break it down to smaller numbers. That's the power of modular arithmetic. And raw algebra, well, I think it's just one notational convention. And we do so because it's our own language, okay? So makes mathematics more interesting when we have something of our own, right? Yeah. So make it more palatable, so to speak. Yeah. Okay. Okay. Let's take 5 minutes break. And when it comes to binomial coefficient, okay, so we notice something too, something else. Maybe not. Maybe something. How interesting. Okay. Let's take 5 minutes break, okay, and then we'll explore this mathematics. Raw algebra, okay, modular arithmetic, which is I find it very interesting. Okay, it's number theory with good application in cryptography, encryption, computer science. Okay, so it's worthwhile to well for us it's entertaining. For future generation, very educational, worthwhile to teach them. Okay, all right, we'll take 5 minutes. Okay. Okay. Well, we are learning quite a bit, huh? Fermat's little theorem. Wow. Okay. Oh, there's so much to it. Okay, so we are just working our way up, right? So a lot of lemmas. What is lemma? Little theorems, small theorems. Okay, so like Lego blocks, right? Comes in a machine like car. You have many different parts in a car. You have exhaust pipes. You have some filter, air filter, and you have engine. You have tires, windows, window motors, right? You have like this automatic shift, gears, and whatever, right? Yeah, mathematics like that is like big machinery. Okay, they're small parts, and we call them lemmas. These are small theorems. All right, so you have NCR, right? Is equal to n factorial divided by n minus r factorial times r factorial. Okay, and when n is PCR, p is prime number. Okay, p factorial divided by p minus r factorial. And this is the whole thing turn out to be p times some number m. We'll call it prime binomial coefficient lemma. We should give it a name. Okay, prime binomial coefficient lemma. We gotta give it a name, right? So okay, proof. We know p factorial rho p is 0, meaning, well, there's some mathematical notation. Yeah, p divide p factorial. Okay, but yeah, this notation is good, but it's a little bit confusing. Okay, so we just stick with row algebra notation, row notation. Okay, so yeah, because p factorial is because this is because, okay, this is therefore, right? And upside down triangle, that's three dots, that means because. Okay, because p factorial is equal to p times some number k, and if we do the row p in both sides, p times k, well, because, well, comma, okay, p factorial is p times p minus 1 times times 1, right? So it's p times some number k, and when we do row p on both sides, and by definition, p times k is a multiple of k, p, so row p, yeah, is 0, right? So that's that. Division, huh? Well, we have multiplication, right? Whew. How challenging. In modular arithmetic, is there any property about division? I'm kind of wondering. So let me look it up again. Let's go to brilliant.org again. Is there something about division? Yes, there is. Okay. It says it's tricky. Okay, okay. All right. Yeah. Well, let's think of it this way. Okay, so I'm fumbling. Okay, so your p factorial is equal to p times p minus 1 factorial, right? So we divide by p minus r factorial. Okay, to this PCR. Now, we know from Pascal's triangle, which is like recurrence relationship between binomial coefficient, okay? They're all integers, right? Binomial coefficients, whether p is prime number or not, NCR, they're all integers, positive integers, natural numbers, when we construct this Pascal's triangle, okay? So, we know p is an integer, positive integer, natural number, right? And so this whole thing is an integer, and that means this part has to be integer as well. It cannot be a fraction. Why? Because when it comes to like group theory, okay, just a little bit, right? Integer is closed when it comes to multiplication. Okay, so p times some number, this have the whole thing is a natural number, positive integer. All right. Meaning somehow, some way, there should be some canceling out, so it does not become fraction. The rational number. Okay. Yeah. Now the question is, will this p disappear somehow? No. Why? Because p is a prime number, and p minus r, there's a number less than p, and r is also some number less than p, and it will not have any common factor because p is a prime, right? Yeah. A number less than p cannot divide p because p is a prime number, right? Okay. Yeah, so that's the proof. P times n, some integer. Okay. And this whole thing has to be an integer because uh, the result of this whole thing, binomial coefficient, has to be an integer, and integer is closed, like integer times integer is always integer. Okay. Inversely, if the result of integer, if result is an integer, and if with the multiplication of some numbers, then those two numbers also has to be integer. Well, not necessarily, but in this case, yes. Why? Because p is a prime number. Okay. Yeah, I know it's kind of messy. Well, welcome to mathematics. Well, my mathematics is very poor. Okay, it's very low quality. Okay, so I'm just a fan. Right. We are learning something, right? Yeah, well, that's good. Let's take 5 minutes break, okay, and then we'll look at it again. Okay. Yeah, prime binomial coefficient lemma. Okay. Yeah, we'll take a look at it again. Okay. All right. We get there. Okay. So. Oh boy, difficult. Okay, couple of things. But Pascal's triangle, okay? Yes, recurrence relationship, right? There's a lot to this, all right? So NCR is equal to n minus 1 C R plus n minus 1 C R minus 1. Is it minus 1 or plus 1? Oh my goodness. Okay. You have, yes, yes, yes. Right? And you have 0C0 starting case, okay? 0C0 is equal to 1C0 is equal to 1C1 is equal to 1. That's the initial triangle in binomial coefficient, Pascal's triangle. Okay. Therefore, NCR is a natural number. Always. The construction, the recurrence relationship of Pascal's triangle. Okay. Binomial coefficient is always an integer, positive integer, natural number. Okay. I'm sorry, it's difficult to see, right? Let me bring it closer to you. Right? Yeah. Now, we're still trying to prove this prime binomial coefficient theorem or lemma. Okay. Yeah. PCR being always some multiple of P. Okay. Except the very first term and very last term. Right? So there should be some condition here. R is more than 1 and less than P. Uh, no. Index start from 0. So more than 0. I could be 1. Okay, so yes, yes, yes. Yeah. Huh. We grab another whiteboard and prove this prime binomial coefficient theorem. Let's call it theorem, okay? Because it's something very cool. All right. Um, we grab another whiteboard and formally prove this. Okay. Yeah. So, but let's make a sketch. Okay. So we're trying to prove this is PCR is a multiple of P. Okay. Like basically, we're trying to prove PCR rho P is equal to 0. Okay, so that's what we are trying to prove here. Okay. Okay. All right. It all boils down to proving this guy. Is this guy an integer or is a fraction? Okay, that's all it takes. All right. Yeah, we are making a different approach to prove this. Okay, so we know the result PCR is an integer. Okay, and now we have a number times a number is equal to an integer, right? But first number that appears in this multiplication is a prime number, right? So it does not have any factor, right? And here you have bunch of in the denominator side, we have bunch of multiplication like factorial, right? But all of them are less than p, right? Because r is more than 0. Okay, so all these numbers downstairs is less than p. Okay, and eventually, so you cannot cancel out p. All right, so but it will cancel out all the upstairs guy here inside of this box because this number has to be an integer. It cannot be a fraction. Okay. Why? Because if it is fraction, then we are into trouble. Why? You have fraction times prime number. So the result, I'm sorry, oh my goodness. The result, p times some fraction, will be not be an integer. Okay. So that's why this one has to be an integer. Okay. 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 Ah. Yeah, it's kind of too much hand waving going on. Give me 1 second, okay? this external hard drive is making some noise. I don't know what's going on. Okay, it stopped making noise. Okay. Okay. Let me unplug that external hard drive real quick. Okay, so because I'm not using it. Clicking sound is distraction. Okay, so okay. All right. Well, basically that's that. Okay, so well, we take 5 minutes break and we grab another whiteboard and we get to the bottom of this thing. All right. Yeah. Okay. All right. Let's take a break. What a mess. I'm sorry. Oh boy. Okay. Wow. Mathematics, huh? Whew. Wow. Difficult. Ah, what a mess. Oh boy. Let's take a break from mathematics. All that math, all that mess, right? Why don't I sing your song, okay? Yeah. So some part of this song was who was the singer? Yeah, it's a band named I think they're from Massachusetts. American band, rock band, independent. It goes like, darling, loving you is such an easy thing to do. It's such an easy thing to do. So let me do it. That's that. Dun, 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 dun. Love that song. Darling, loving you. Ah, yeah, we sometimes we love mathematics, but I don't think it's very easy to love mathematics at all. Sometimes it's kind of difficult. Whatever. So, in mathematics, group theory, okay, there's what's called closedness on operation. For example, addition operation is closed. Integer. Natural number is closed when it comes to addition and also multiplication. Okay, closeness meaning if a and b are natural numbers, that means a times b is also natural number. Okay, it belongs to a set of natural numbers. Also, a plus b is also natural number. Okay, so that's what they mean by closedness. Yeah, natural numbers are closed in terms of addition and multiplication. Okay, so that's what they mean by closedness. But they are not close when it comes to subtraction. It may not. Okay, so or division. If you subtract two natural numbers, it may become negative number, which is integer, not natural number. Okay, and if you divide two natural numbers, may become fraction, which is not a natural number. It's not even integer. Okay, so yeah, natural number is not closed when it comes to division or subtraction. Okay, so that's what they mean by closeness. All right. Okay. Let me drink a little bit. I cannot do mathematics without drinking. Okay. Well, I haven't been drinking so far. It's been almost 2 hours, right? Yeah. Yeah, my body has been detoxed, so it's good. Okay. All right. So, because of binomial coefficient relationship, okay, NCR, right? And the initial point, yeah, Pascal's triangle, right? Meaning, and because natural number is closed when it comes to addition, therefore, NCR is also natural number because it's all, and the bottom line, one, okay, Pascal's triangle can be constructed with just addition of positive numbers, integers, natural numbers. Oh, and that's the beauty of Pascal's triangle, right? Yeah. So yeah, NCR binomial coefficient, they're all integers, they're positive integers, natural numbers. Okay, let's give it a name. Binomial coefficient in natural number theorem. Okay, so we have that. We've just proved it informally. So okay, yeah, it's because addition of two natural numbers become natural numbers, right? Yeah. Okay, we're building up one by one, like Lego blocks. Okay. Next, in a special case, PCR is a natural number, okay? Because P is just prime. In general, NCR is a natural number. And then so is PCR. Why? Because P is a subset of N. Number of set of primes is subset of set of all natural numbers, right? Positive integers. Okay. So we know this is natural number. Okay. It belongs to the set of natural numbers. Okay. We know that. Now, PCR is equal to p factorial over p minus r factorial. Okay, so just formula, right? Which is equal to p times p minus 1 factorial over, right? Now, let's look at this number. Is this an integer? Is this a natural number or not? That's the question, okay? Because hypothetically, it could be a fraction, right? If it's a fraction, that means there's, okay, we're gonna prove by not counter example, but what's that called? Contradiction. Okay, proof by contradiction. Prove that this belongs to natural number. Let's prove it. Okay, we do proof by contradiction. Okay, proof by contradiction. Assume this is not a natural number, but let's assume it's a fraction then. Where n is not multiple of m, meaning n row m is not equal to 0. Yeah, same way of saying m does not divide n. Okay? So when n is divided by m, there's some remainder, which is not 0. Okay? Yeah. So it's not a natural number, but it's a fraction. Okay? So, meaning there does not exist k, which is a natural number, such that uh, n is equal to mk. Okay? Yeah, exist, not exist. Okay, that's just fourth order logic notation. Okay. I mean, this is how I learned mathematics in Seoul, South Korea back in 1990s. All right. So, all right. If you assume that, okay, this whole thing we call it L. We don't want to rewrite all this stuff. So this is P times L. Okay. So if you assume that, all right, then this whole thing is L. So then, okay, well, sorry. Then PCR is equal to P times L, which is equal to P times N over M. Okay. Now, P is a prime number. So M is a fraction, N over M is a fraction. That's what we assumed. Okay. It's not a natural number. Okay. And now we are in trouble. Why? Because, look, M cannot disappear. It's in denominator. And we assume that it's a fraction. Okay. Then P and M, it has to cancel out somehow. Why? Because it has to belong to natural numbers. Okay. But P is a prime number, right? By assumption. So this cannot be a natural number. So M cannot disappear because P is prime number. it has no common factor with them other than one. Okay. So yeah, now we arrived some contradiction here. Okay. So therefore, and that's contradiction. Therefore, L has to belong to natural number set. QED. Okay. Woo! We got it. We proved that prime binomial coefficient theorem. Okay, so yeah, yeah, that was tough, huh? Yeah, it was. But some important condition though. Okay, so R has to be it could be one, but it cannot be zero. Okay, so and strictly less than P2. Okay, because yeah, why? Um, because if R is zero, what happens? PC zero is one. Okay, yeah. So that's not a multiple of P. Okay. PCP, that's also one, which is not a multiple of P. Okay, so if R is 0 over P, then this whole thing, L, has to be 1 over P. Okay, because PCP is equal to PC0 is equal to 1. Okay, which is not a multiple of P. Okay, it's that's like by definition. Okay, it's a binomial coefficient by definition. Okay, so that's why I cannot be 0 over P. Okay. Whew. It's already known. Okay, all these things that we've just proved is already known as a part of this proof of Fermat's little theorem. They just didn't name it. They took it for granted. But it's not easy for us. At least not to me. It was not obvious. It was quite a surprise. So we proved it formally, and we gave it a name: prime binomial coefficient theorem. Okay. They kind of proved it, but they, because they're professional mathematicians, they just kind of took it granted. But it wasn't easy for us, at least not for me. Okay, no, it wasn't. Mm. But we got it. Okay. Now we'll take 5 minutes break, and let's get back to prove that Fermat's little theorem, special case. Okay, we may as well just prove Fermat's little theorem. Okay. Why are we doing this? Just for fun, right? Yeah. I apologize if this is not entertaining for you. Okay, but at least we are trying to educate the future generation. Let them learn mathematics. At least it keeps us out of trouble. We are not drinking and driving. We are not going to protest. Eh? We can still have fun doing mathematics, right? Yeah. It's a good hobby, okay? So, yeah. And also, it doesn't cost any money, right? If you have hobby, it costs some money, right? But when it comes to mathematics, it costs a lot less than comparing to other hobbies. Okay, so yeah, some poor man's hobby, mathematics. Okay, so look, exercise in U.S. Army. Okay, push-ups and sit-ups. Yeah, calisthenic pull-ups. Okay, upside down sort of push-up. All you need is just floor, wall. That's all you need to do exercise. Okay, because going to gym membership, that's expensive. Okay, so Army has no money because this government or federal agency, U.S. Army. Politicians, I think they are doing fine job. Okay, they want to save taxpayers' money. Okay, so U.S. Army, yeah, we just do push-up, sit-up, 2 mile run. That does not cost any money. Okay, we take 5 minutes break. Okay, so we got it. Okay, yeah, and then yeah, we fry the bigger fish. That's very much little theorem. Okay, we get to that. Okay, so we are kind of ready to do that. Right. So. Let's take 5 minutes. Okay. So. Oh boy, we are working very hard. Okay, so that's good, right? Okay, let's grab brand new whiteboard, all right, and then go ahead with this proof of Fermat's little theorem. Yeah. special case of Fermat's little theorem, which is more interesting than more generic version. Okay, we're gonna prove. Yeah, this guy. Okay, so yeah, that's more interesting for us. Why? In raw algebra, okay, it's quite surprising, right? P is a prime number, okay, and R is a remainder. PP cancels out. We may call let's give it a name. Let's call it cancellation theorem. It's a special case of Fermat's little theorem, okay, but it's more interesting than general case, okay. PP they just cancel out. P's power also is prime number, okay. R is remainder less than P, okay, zero or more, right? PP they cancel out. It's quite surprising. Okay, it's a special case of Fermat's little theorem, which is already proven by somebody else. Okay, yeah, it's exotic, right? That's why we are doing this. There's some beauty there. Cancellation. Let's call it P cancellation theorem. Oh, how interesting! Wow. You know what? Let's take a break from all this. Okay, so because we are ready to prove this, it's just a matter of time. Okay, so we are ready to prove this thing. I was in the U.S. Army. Okay, so yeah, back in the days, we had drill sergeants, right? Would give us hard time. Not to me though, because they really liked me. Okay, so let me take some selfie. Okay, I kind of like this hairdo. Hawaiian t-shirt. Okay, so uh, good enough. Yeah, U.S. Army, they want to save some money to taxpayers. Okay, so low budget exercise, push ups, sit ups, body weight. Okay, because dumbbells, it costs money, right? You don't need dumbbells. You don't need bench press, running machine, running mill. You don't need that. Bicycle, it costs money, right? So yeah, politicians, they want to save money to taxpayers. Okay, I think they're doing a fine job. Yeah, go out there, run, cost no money. All we need is some safe trail so that we can run on it, right? Push up, sit up, all we need is a floor, some space. Yeah, home exercise, okay? Yeah. Doesn't cost that money. Mathematics, all we need is whiteboard and pen. It does cost some money, but not too much. This whiteboard in Walmart, how much was it? I guess like $15, $20, something like that. Pens, set of pens like $5. Okay, so and you can reuse it again. Yeah, eraser $1, $2, whatever. Okay, you can erase again and again. But pencil and paper, yeah, you don't want to quite erase that pencil and paper, right? It makes a mess, right? So, but in the whiteboard, it doesn't make any mess. It's recyclable, reusable. It's better, right? So yeah, drill sergeants, they liked me a lot. Okay, so because we're about the same age. Some drill sergeant probably was younger than me. I joined the U.S. Army 2009. I was 31. Okay, so I was born in 1978. Some drill sergeants were younger than me, so they liked me. Okay, but some other guys, okay, yeah, they were stressed out. I was like, yeah, whatever. I have met some ladies who are kind of like drill sergeants. Yeah, very mean, rude. Okay, they will give me some hard time. Okay, some ladies are like that. Okay, I'm like, whatever. It's good training. Okay. Oh yeah, lady. Yeah, you kind of remind me of my drill sergeants. Okay, so mean and rude. It's good training. Okay, yeah, I tolerate you. Because some guys hate women, and I'm like, there's no need to hate anybody. I met some mean, rude ladies. Okay. Yeah, but hey, you kind of remind me of my drill sergeants. You're mean, rude. You have good training. Okay, I tolerate you. Because like Friedrich Nietzsche said, yeah, what does not kill you make you stronger. Okay. Yeah. Okay. There's no need to hate women. But some other ladies, they're so nice. But at the same time, they're mysterious. Okay. We guys, we don't understand women. Okay. Women, yeah, they're just different kind of gender, right? So we guys, we just want women, but women to women, one man. I don't know. I guess it depends on individuals, right? I guess some ladies want men, some ladies don't. I don't understand women at all. Okay, that's why I'm single. Okay, okay, we took enough break. Okay, but I'm a huge fan of women. Okay, just like mathematics, I'm just a fan. Like martial arts, dancing, I'm not good at it. I'm just a fan. I love mathematics, martial arts, dancing. Although I'm not good at it, just like that, women, I don't understand them. I'm not good at communicating with them, but I don't understand them. I'm just a fan. Hmm? Just a fan. All right. Okay. You ready? Let's do it. Let's grab a pen. Yeah. Ah. Let remainder be p minus k. Yeah, k more than 0. Okay? Less or equal to p. Okay? The remainder can be 0, right? Yeah. But r is strictly less than p. Okay, so k has to be more than 0 and less or equal to p. Okay? Right. Then no, we are not doing the right. Yeah, sorry, we have to do this mathematical induction. Okay, so mathematical induction. Okay, so mathematical induction. First case, r is equal to 0, right? Then left hand side, 0 to the p, rho p is equal to 0 rho p. What is the remainder when we divide 0 by p? What's the remainder? 0. And r is equal to 0. Okay? 0 here. It's just same as the right hand side. So that's good. Okay? In your case, satisfied. Okay? Now, let's say r is some k. Okay? So we want to prove mathematical induction. Okay? K to the pth rho p is equal to k. If you assume that k plus 1 to the pth rho p is equal to k plus 1, right? If you assume that, if this is true, we don't know, okay? Yeah, this is arrow, propositional arrow, okay? If then, if A then B is proposition, okay? So mathematical induction, okay? So we call the left-hand side of this propositional arrow, we call this L, left-hand side. Right-hand side of propositional arrow, we call it R, okay? All right, so note, note that, observe, okay? K plus 1 to the pth, binomial expansion, okay? So k to the pth plus 1 to the pth uh, plus binomial coefficient. All right. Oh my goodness. Let's rewrite this. Okay. Okay, so we have these middle terms where NCR, okay, where PCR, where R is from 1 to P minus 1, all right? And so prime binomial coefficient theorem, right? We know this is, whole thing becomes by prime binomial coefficient theorem, where L is some natural number, okay? Okay, now, let's take this rho P on both sides of the equation, okay? So, right, then right? And we're gonna use distribution theorem, okay? Okay? Distribution theorem, which we already proved, okay? Now, k to the pth, rho p, we assume that that's k, right? Mathematical induction assumption, okay? So this becomes k. P times L rho p, that's 0. By definition of rho algebra. Okay, so 0. And 1 rho p, that's by definition that's 1, because 1 is remainder and p is a prime number. What? Prime number being 2, 3, 5, that's more than 1. Okay? So that becomes 1. Oh? What's left is rho p. Okay? Now what? What is k? What's the range of k? Okay, okay. K is like R, right? So yeah, k is just like R, right? So 0 k p, right? Okay. K is less than P, but K plus 1, it could be P. Okay, so can we just get rid of this rho P? I don't know. All right. Well, right? Okay. Whew. Yeah, there's some obstacle there. Okay. We are like off by one. All right. Well, well, we can make two cases. Okay, two scenarios. If K plus 1 is equal to P, then P rho P is equal to 0. Right? And then this is correct. Why? Because P to the Pth, rho P, that's 0. All right? Okay. When if K plus 1 is less than P, then yeah, this becomes to K plus 1. Okay. So when eek, yuck. We have to continue this tomorrow, right? Because we are almost there, okay? But there's just one obstacle that we need to surmount. It's not insurmountable task. We can overcome this obstacle, okay? Somehow, maybe tomorrow, okay? But today, I think we paid enough service to mathematics, all right? Mathematics education. We did enough, okay? So, okay, we take 5 minutes break, okay? So, just one obstacle, okay? Yeah. I did not see this coming, okay? Mathematics. We take 5 minutes, okay? So, All right. No idea. Uh, yeah, let's snap out of this. My brain is saturated. Okay. Mathematics, I don't quite understand. Right. I sleep on this, okay? Yeah. We'll continue tomorrow. That thing, okay. Let's just sit back and relax. It's Saturday evening, right? Let's snap out of this. Let's talk about something else, right? Let's talk about Hollywood. Yeah, let's talk about something more interesting. Yeah, Milana Weintraub. Okay, I think she's cool. Okay, she is a Hollywood uprising, this up and rising, up and coming Hollywood actress, and also very good writer too. Right, a huge fan of that stuff. Yeah, she's cool. So after this morning's episode, which is already uploaded. Okay, nowadays, yeah, the humanology series is caught up. Okay, there's no more backlog. Yeah, so it's like almost online, like live, right? We film this, and couple of hours after filming, it get uploaded. In a matter of couple of hours. Okay, it's very much live, up to date stuff. So that's good. Okay, so Hollywood, yeah. After this morning's episode, I watched this movie Ghostbusters. all-star casting, right? You have Sigourney Weaver, you have Bill Murray. Great, fantastic casting and great story, right? Yeah, written by two guys, also actors. Okay, I don't remember their names. Okay, some like Aykroyd, Mr. Aykroyd, and Mr. Ramis. Okay, yeah, Mr. Ramis, that's the guy with his eyeglasses. Okay, Mr. Aykroyd, he was also in that movie, Martin Point Blank, kind of assassination movie, right? Gross Point Blank, right? Love that movie too. Okay, so very talented actors, actresses, right? Mr. Ramis, he was writer of this Animal House, the National Lampoon, right? Yeah, I remember that name. And he's Jewish. Okay, Mr. Ramis, talented writer. Okay, huge fan. Yeah, Miss Weintraub, Milana Weintraub, she's Jewish too. Okay, European Jewish. Came to America. Okay, so yeah, Jews. I'm not anti-Semitic. They're cool. They're very hardworking people. Some of them very smart. Some of my best friends are Jews. Okay, so yeah, I'm not anti-Semitic. Okay, so yeah. So Miss Milana Weintraub. Okay, she's attractive lady. Very. Yeah, she's like European Jew, so she's like brunette, right? Very attractive lady. Okay, so I'm not a woman. Okay, I'm a man. Asian guy, right? I mean, you have BTS, Asian boys, all boy band. They're young. They're kind of pretty, handsome Korean, Asiatic male. But I'm not that young and I'm not that pretty. Okay, you don't even get to see my eyes unless I open it up for you like this. Okay, so yeah, I try to look nice, presentable. Nice Hawaiian t-shirt, all right, and but mathematics is a challenge. Okay, so I sleep on it. Okay, we are off by one. All right, like k plus one is it? Yeah, because it can become same as p. So we have to do two cases. Okay, k plus equal one is equal to p. You do that, and k plus one is less than p. You do that, yeah, case by case, two cases. We get to the bottom of that thing. Okay, tomorrow. Right now, I'm saturated. My brain is saturated. Okay, so I cannot do any more mathematics tonight. Okay. All right. Let's talk about science. There's some about a year ago. There's some science. It was in the news. Okay, during the Pompeii volcano. Right. Some brain exploded. It became some glass. I don't think so. Glass. It has to do with silicon. It's a mineral. Our brain matter does not have that much silicon. Okay, so this was a lie. Some scientists want to get some attention. Okay, they come up with some outrageous claim or theories. All right, like black hole, special general relativity, Einstein. Okay, garbage science. Okay, junk science, all wrong. Yeah, scientists they can lie too. They are people. People are people, right? Scientists. There's nothing special about scientists. PhDs, physics, even in mathematics. Okay, Well, mathematics, yeah, there's some wrong theories. Like Mr. Gero Cantor, he was Jewish too. Okay, yeah, the Aleph, whatever, this transcendental set theory, infinity. Okay, some of that it was wrong. All right, Mr. Kronecker, yeah, he rejected Gero Cantor's proof. Okay, yeah, Mr. Gero Cantor, he's Jewish, European Jew. Okay, so some of his theory was correct, like diagonal method, very ingenious, very smart. That's cool. Okay, but other than that, Mr. Gero Cantor, he was wrong at some point. So even in mathematics, there's some wrong theories, right? Physics, even more so. All right, for 100 years, all these physicists, astronomers, they've been lying, manipulating data. All right, there's no such a thing as black hole, dark matter. It's just figment of imagination. It's science fiction. All right. Yeah, Mr. Karl Popper, right? Was his name? Yeah, unfalsifiability, right? Yeah, deep in the universe, there's dark matter, there's this black hole, okay? Unprovable, right? It's too far away. They manipulate data, right? There's no such a thing as black hole, right? Unfalsifiable. It's not science. It's more like a religion, right? Junk science, right? So black matter in Pompeii volcanic eruption becoming a glass garbage junk science, all right? No, if glass is a silicone, okay, our brain matter does not have that much silicone in there. It's carbs, protein, fat. It's not Si silicone. No, it does not make glass, right? Yeah, Pompeii, human brain, it pops up, it becomes ashes. Mostly it's carbohydrate, protein, some nitrogen, okay, some fat, so carbon molecule, C, carbon atom, hydrogen atom, oxygen atom, or nitrogen atom, okay. Some calcium is born, okay. Not many silicon, okay, so the theory is a junk science, okay. Pompeii, yeah, some glass. No, brain becoming glass, junk science, okay. Some scientists, they make up these phony theories just to get attention. They crave attention, some of them. Money, power, fame, right? It was published in the Lancet or whatever, pure, top high ranking, maybe Science or Nature. High ranking these scientific journals, peer reviewed journals, but many of them junk science, okay? Garbage, right? Scientists, they're just like any other people. They're just like us. They lie, right? For 100 years, they've been lying about general special Einsteinian relativity theory. Okay, so garbage, junk science. So yeah, yeah. Hollywood, junk entertainment, right? Yeah, mass singer, mass dancer. It's like, is this world coming to an end? The abomination, right? Like Book of Revelation, right? So ugly. Oh my goodness, horrible. Some Hollywood people, okay, they come up with the worst possible idea. Just like Washington D.C., okay, yeah, President Trump, President-elect Biden, coming up with the worst possible ideas, right? Hollywood, right? People up there, right? Celebrities, the stars, celebrities, celestial bodies, right? People up there, Washington D.C., Los Angeles, California, Hollywood, who get all the media attention. Many times they come up with the worst possible ideas, right? Horrible, right? Back in the days, Manhattan, New York, okay, yeah, Occupy Wall Street. Nowadays, yeah, Occupy Washington, D.C., BLM or pro-Trump protesters, Occupy Capitol, right? They may come a day, Occupy Hollywood, all right? I'm not encouraging them to occupy Hollywood. Hollywood is already occupied. There are a lot of homeless people in Los Angeles, California. Okay. I mean, yeah, starlets want to be the star. I was one of them, but I had my job. Right. We take 5 minutes, okay? Then I tell you some of the Hollywood stories I experienced. Okay. Okay. We take 5 minutes. We'll stop and restart. It's been already about 3 hours. Okay, so okay. We'll stop and restart. See you soon.